All right, so we're going to learn about the geometric distribution. It's really, in terms of the conditions, it's really the same as binomial, except instead of a fixed number of trials, you have a variable number of trials. Okay, so if you've been taking the time to memorize those four conditions for a binomial distribution, fixed number of trials, fixed probability, independent events, and two outcomes, then it's an easy transition because it's variable number of trials, fixed probability, independent events, and two outcomes. All right, so it's pretty manageable when you think of it that way. But it does require that you have committed the four conditions for a distribution that's to be binomial. You commit that to memory.
So is it not just the opposite of the binomial? It's just the opposite of it?
Just opposite of the first rule. Just that first rule. The other three are the same.
Okay.
So instead of fixed number of trials, it's variable number of trials. Everything else is the same.
Okay.
Yeah, which really kind of lends itself to like a nice multiple choice question. Which of the following is not a condition? And so you can be rewarded in that regard. That's not really a hint situation. It's just more like a direct statement that I put a question like that on the test. Right, so a multiple choice question related to the four conditions, and it'll be something along the lines of which of the following is not a condition for a binomial distribution or a geometric distribution, and so you go from there. Right. So that's what really all of this is talking about. I threw in some examples there, just some contextual cases. Basically, when you're dealing with the geometric distribution, you're looking to establish the number of attempts that it would take before you have your first success, and then find the probability of that. So the examples: flip a coin until you get heads, roll a die until you get a 6, throw darts until you hit the bullseye. All right. I did a kind of a guided example here. There's a little context here that I never got around to taking out. So I'm going to just cross that out because it doesn't make sense. Because we did not do a simulation, at least not directly. We actually did. It was the randomizer on Google Sheets, but it was so long ago that I can't directly reference it here. Find the various probabilities associated with a dice simulation. I don't know. I'll rephrase that at some point. But basically, it's this and this that need to go. So if you need a typo bonus as the marking period comes to an end, that may be something that you can take advantage of. The probability that a 6 will come up on the first roll is 1/6. So when we say x equals 1, we're saying that you had your first success on your first trial, right? So you rolled the die, and you got a 1. You got a 1 as a result, which is 1 out of 6 probability. All right. So in my table here, I'd have a 1/6 for that first outcome. The probability that a 6 will come up on the second roll is the probability that it didn't come up on the first one, and then it came up on the second one. So that is established here, where I'm saying I got something other than a 6 on the first roll, so 5 and 6 probability, 5 out of 6. And then I got the 6 on the second roll, so 1 out of 6 probability. Right? So that's 5/6 times 1/6, which is 5/36. Folks, no need for laptops. This is a lecture day. So for the third case, it's the same idea. We had 2 failures followed by a success. So 5/6 times 5/6 times 1/6, which would be 25/216. And then we would just continue the progression. So that 5/6 could be thought times 5/6 could be thought of as 5/6 squared times 1/6. Right? So this one could be thought of as 5/6 to the first multiplied by 1/6. And this one, just kind of working backwards, there was no 5/6 there. So that 5 over 6 must have been raised to the 0th power because there were 0 instances of which there was a failure times 1 over 6. So that kind of brings us the rest of the way where we would say, I guess I'm going to write small here, 5 over 6 to the 3rd power times 1 over 6. 5 over 6 to the 4th power times 1 over 6. And then the n rule. So if you look at the comparison between the first success and the power associated with failure, it's always minus 1. All right. So we're looking at 5 over 6 to the n minus 1 times 1 over 6. Now that's specific to rolling a die, but we want to be able to generalize this for more than just that. All right. So that 5 over 6 was the probability of failure. Right? The 1 over 6 was probability of success. So we typically refer to failure as either Q or 1 minus P. All right? So I'll write it both ways. So I could say Q to the n minus 1 times P, or 1 minus P to the n minus 1 times P. All right, so either of those will get you a probability distribution that's geometric in nature. Just refreshing my memory. Let's see. They do give you that on the AP formula sheet. All right, so that's nice. They give you the formula for binomial probability. They give you the mean and standard deviation of a binomial distribution, so things that you don't need to remember. Geometric distribution, and we'll get to it in a second, but they also give you the mean and standard deviation of the geometric distribution.
Does it say Q or 1 minus P on the sheet?
It says this one. All right, so what I'll do really quickly is just kind of take you through the look of this distribution. All right, you can see really, I mean, anytime, if you need typo bonus, anytime you see one of these little boxes there, that's a typo. It's just a question of what's supposed to be in place. So mu and sigma. All right, so we could actually compute the probability distribution's mean and standard deviation by making a table or using these formulas. All right, mu, and it's not really clearly written here, so I'll write it again. Mu is equal to 1 over p. And sigma, well, I gave the variance one, but sigma is equal to the square root of 1 minus p over p. All right, so we'll just verify that real quick.
Is the radical of the whole thing or just the top?
Just the top. Just the top, yeah. All right, so I'm going to go into statistics. I'm going to make my table going from 1 to some large value. It really doesn't matter. I mean, obviously, we don't have to go too far to get an idea of what's going on with the graph. So I'll go maybe 1 to like 20. All right, so remember the shortcut way of putting in the values, consecutive values, starting at 1 and going to whatever number you want, caps off at 100. Hit OK. Fill with a formula, select that first option. You see it says integers from 1 to 10. So you just change this upper bound to whatever you want, right? Again, short of 100. So I'll go 25. All right, so I'm going to hit OK. And that puts in the numbers 1 to 25, which is great. Didn't have to worry about doing that. I can also get the probabilities associated with that by plugging in my formula for the probability distribution. All right, so I hit OK, fill with a formula, empty. Have a look. Every now and then you'll come across a formula that you're like, oh, I didn't know that was in there, and I can make use of it, but probability ones haven't really made their way in there. So I'm going to do, it's 1 minus p, so this is the roll of a die, so 5 over 6. I'm going to raise that up to the n minus 1 power. N is the value that's stored in value v1. So shift alpha division 1. And then put in a 1 divided by 6. Oops. Put in a 1 divided by 6. And that'll populate our entire list N1 with the appropriate probabilities in
Wouldn't, would it, wait, I thought it was V1 minus
V1 minus 1. Thank you.
1.
All right, so these values go in V1. Then in N1, you're putting in, let's see if I could kind of squeeze it in here, 5 over 6 to the V1 minus 1 times 1 over 6. All right. I'll show you a little shortcut in a minute, because as we become accustomed to, we know that in the distribution menu, there's some kind of shortcut associated with each of these probability distributions that we're learning. So we'll get to that in a sec. Hit OK. It puts in our probabilities. At first glance, you're like, oh, a bunch of decimals, but at least the first one matches up. Most people recognize that 0.16 repeated is 1 over 6, but maybe you don't. If that's the case, then maybe you just, in a separate list, kind of verify each, the first couple. So the first one should be 1 over 6. That's correct. 5 over 36. That's correct. Bless you. 25 over 216. Bless you, bless you. That one is also correct. So the first 3 are correct. Doesn't mean that everything's going to be correct, but there's a good chance that they are. All right. So what I'm going to do now is go to stats, go down to the mean. All right. Now, obviously, the larger number of trials, the closer we get to the true nature of the distribution. But this is saying that the mean of this geometric distribution is about 5.735, and the standard deviation is about 4.828. All right. Now, what the probability should be, what the mean should be is 6, because the formula for the mean of the distribution, the geometric distribution, is 1 over p, and p is 1/6, so 1 over 1/6 is 6. All right, so my 25 trials, it got me in the neighborhood, but I would imagine I'd have to go out a few more in order to get to the true probability. All right, I keep saying probability, I mean mean. So I'm going to go back into data. And this is something that it must be in the new update, because it wasn't like this before. So I put in the first 25 values. Let me up that, fill with a formula. It recalls now. In previous updates, it wasn't like that. It would just kind of ditch whatever fill with the formula was there. So now it allows you to actually update it, which is cool. So I'll go up to 100. And you'll see that it stops giving the probabilities. Stops giving the probabilities after the first 25 values. But if I go into frequency N1, fill with a formula, it recalls my previous operation. So if I hit OK again, it'll recompute for the remaining values. Right? So that it must be something in a new update, but I'm grateful for it. So go to stats, and now you could see that the mean is much, much closer. All right? So this is when n is equal to 25. When n is equal to 100, mu is approximately 6, and sigma is approximately 5. Well, I would probably round that to 5.5, but 5.477. All right, so I can verify that with my formula. 1 minus 1/6 under the radical divided by 6. Got to go into my calculation app to do that. 1/6 on the bottom. I'm like, what am I doing here? About 5.4. So that one actually checks out pretty good. All right. So this other stuff here, the variance, all that is my standard deviation squared. All right. So that's not something that I think we need to worry about too much. Anything else in here? Yeah. So quick example, and through this example, I'm going to show you the shortcut. So a basketball player typically makes 90% of his free throws. He takes several free throws during a game. What is the probability that he makes his first free throw on his 7th attempt? Right. So it's actually, honestly, I would say, easier than the last couple of pages made it seem. In fact, I asked a question on the first, I think it was the first unit test for probability. It was in the review. It was on the test. It was like, what's the probability that, I forget what the context was, but it was, you got your first success on the last attempt. You know, and it was like, I just figure out the probability of not succeeding 9 times, and then the probability of succeeding, I think it was like a coin flip or something. So it was geometric probability. In fact, we did binomial probability in the first half of the unit. We just didn't know what it was, what the name was and what the conditions were, but they were all there. It's just a matter of kind of formally addressing it. All right. So my first success on my 7th attempt, probability of success, 0.9, probability of failure, 0.1. That means if I'm going to have the probability of x equals 7, that means that I failed 6 times and then I succeeded. All right. Now, if you're a 90% free throw shooter, you should expect it not to take too long before you succeed. All right. If you're a 90% free throw shooter and you're playing in a, just a typical regular season game, and you've taken like 7 free throws, like there is an element of coming due, because you're due to hit one because you're historically a 90% free throw shooter, unless there's some issue like an injury or something like that. I call it the Graham Gano. All right, so we're looking at 9e negative 7, so it's 0.00000009. All right, so these are actually nice numbers, so it kind of stands to reason. Now, if you're doing this in the distribution app, so I go into Toolbox, Probability, Distributions, Geometric, all right, just like binomial, we have geometric PDF and we have geometric CDF. All right, this is for a particular instance, so it's an equals case. So probability of x equals m is equal to geom PDF MP. All right, so my m is 7. My probability of success was 0.9, so geom PDF 7.9, and it'll give you the same answer. All right, so it's a nice feature, but this is one of those instances. I mean, you go back and look at the binomial probability formula. That one's got a lot of stuff going on, a lot of substitutions that would need to be made. But here, I doing it by hand, doing it using geom PDF, I feel like it's the same number of keystrokes. Like there's really not much to doing it by hand. So I usually default to doing it that way rather than going into a list and finding it. I, for whatever reason, did not include a CDF example. So let's say, what's the probability? So example, find the probability that he will make his first free throw. We'll just say X is Well, 7, I've used 7 as a benchmark, so I'll say X is greater than 7. Right? So this is basically saying what's the probability that it will take more than 7 attempts for him to make his first free throw? Which, if you're a 90% shooter, this should be very, very rare. Right? So just like I did yesterday, I'll do a number line, but I'm not doing that because that's necessary work to show on the AP. I'm doing it because I want you to understand where the logic is taking us. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. If I want more than 7, I want this group here. It's not locking in. Undo, undo. Come on. I need you to lock in here. There we go. So I'm going to figure out the probability of the stuff we don't want. This is probability X is less than or equal to 7. So that's a geom CDF. All right. I would not expect you to find the probability of each of these things individually and then add them up. If you were to go that route, you would do it using a table. It wouldn't be individual computation. All right. That would be an incredible waste of time. So toolbox, geom CDF. Still with a 7, still with a 0.9. That gives us a 1. Oh, I didn't even know it did that. Right? So it's not really a 1. It's virtually a 1. So I'm going to put an approximate symbol here and say that it's about 1. But it's not a guarantee that you're going to make the free throw in the first 7 shots at some point, your first free throw. But it's virtually guaranteed. I mean, you're a 90% free throw shooter. It shouldn't take too long before you make one. All right? But that's not the question we were being asked. Probability that X is greater than 7 is going to be equal to 1 minus the probability of X is less than or equal to 7, which is going to be approximately 0. That's saying that it's virtually impossible for it to take more than 7 attempts before you make your first free throw. And again, just thinking about the success rate, that should feel correct, right?